Our next presenter is Dr. Pedram Mahzari. He is a research associate of reactive flow in porous media in earth science at University College of London. He has bachelor, master, and PhD degree in petroleum reservoir engineering, and he has been the lead researcher of experimental and modeling studies in EOR and reactive multiphase flow through porous media. Dr. Pedram has also worked with the Science Clean Energy Consortium for advanced characterization of shale oil and gas reservoir and reactive flow modeling for geothermal reservoir in Iceland. And his research interests are EOR in shale oil and gas, characterization of reactive flow in underground reservoirs, and multiphase flow for EOR scenarios. In his presentation, Screening Suitable Crude Oils for Low Salinity Water Injection, Dr. Pedram will tell us how characterizing fluid interactions through micro-dispersions can screen crude oils for low salinity water injection. Thank you very much, Dr. Pedram, for being with us today, and thank you very much for your presentation.
Hello, everyone. My name is Pedram Mahzari. I'm a research associate at University College London, and today, in a few slides, I'm trying to show a mechanism called micro-dispersion formation as a capability to screen suitable crude oils for low salinity water injection. So in this talk, you'll see the results from sandstone reservoirs, carbonate reservoirs, basically a series of laboratory experiments at core scale and fluid-fluid interaction tests to validate our understanding about the role of micro-dispersion formation and fluid-fluid interaction for efficient low salinity water injection. The outline of my presentation is we will have a very brief introduction about water injection in oil reservoirs and enhanced oil recovery. Then I'll briefly overview the rock and brine and oil brine interactions. Then I'll show the summary of the results of the series of core scale experiments on sandstone and carbonate formations. And then after that, we will have our conclusion. As a background and introduction, low salinity water injection has been in the industry for more than 3 decades, and there's a consensus that the wettability alteration is the main cause behind the additional oil recovery, and it leads to detaching oil from the surface. However, what is debatable is the mechanism behind the wettability alteration, and it is a very crucial factor in determining whether the low salinity water injection is going to work. So the cornerstone of the low salinity effect is wettability alteration and enhanced oil polarity. And the oil polarity can be determined by asphaltene and resin content and acid-base components. So as this illustration shows, the oil can cut through the water film and adhere on rock surface directly. So if low salinity wants to change the wettability, it should detach this oil which is connected, which is adhered on the rock surface. And what we think, and in the next couple of slides, we will see the evidence for that, that the dominant fluid-fluid interaction happening between oil and brine can change the oil polar characteristics. So in this slide, you can see that from the right, there is a micro model image showing that when we inject low salinity water, these bright ones are water, low salinity water interacting with the oil. There are some dark spots forming within the oil. Then this on the middle image, you can see that this very brownish phase formed between the oil and the low salinity water. This is called micro-dispersion, which is the dominant fluid-fluid interaction process happening between low salinity water and crude oils. And we have taken samples from this brownish phase and we have analyzed it through ESEM, through FTIR, infrared analysis, and also Carl-Fisher titration, and we identified that this is a packet of water surrounded by oil polar components in a very nanoscale sizes. So in the next few slides, you'll see the body of evidence that we are presenting to show the impact, the dominant impact of fluid-fluid interactions in sandstone and carbonate rocks. What we basically did is we used the same rock, but various crude oils. And if our results were convincing, this would show that there is a chance that if we have the crude oil, if we can identify these micro-dispersion and oil polar components, that we are able to screen the positive crude oils for low salinity water injection. So here we have, firstly, we are showing the sandstone results, and they are taken from this paper published in 2019 SP journal. So for our methodology, we have used same reservoir, sandstone reservoir rock. This is an ESEM image of the rock showing that we have clay, and the clay content of the rock is average of 5% for the cores. And this is a 4 sample cores that we have. We are showing their properties. You can see that they have 20% of porosity, around 100 millidarcy of permeability, and the initial water saturation that we have established was around 10%. So for the fluids we use in this set of experiments, we use 16 different crude oils, and this is a list of the original crude oils that we have used. And in order to make the more crude oils, we have blended crude oils, and we have also pre-contacted crude oil with low salinity, and we remove the micro-dispersions, and they call treated crude oil. And also we use the original oil unadulterated crude oils. And also we have also used, we mixed the crude oil, blended crude oil with the negative one and the positive one, i.e. negative one is the crude oil without micro-dispersion, positive one is a crude oil with plenty of micro-dispersions. And for the brine one, we kept it same for all experiments. The high salinity brine is 100 ppm, and for low salinity brine is 500 ppm, and it has monovalent and divalent. For all experiments, we have first desaturated the core with high salinity water, then we injected, we established initial water saturation, then we aged the core for 3 weeks under pressure and temperature. Then firstly, we displaced the crude oil with high salinity water, which is called secondary water flood, to reach the residual oil saturation. And then we switched to low salinity water injection to recover the remaining oil, as it called tertiary water injection, tertiary low salinity water injection. And this is the temperature and pressure under which we performed the experiment. So here we're showing just the results of the tertiary low salinity water injection for those interested in secondary water flood and the spontaneous imbibition experiment that we perform on these cores. They can be referred to the paper published in SP journal for these set of experiments. So this is the results of the 16 crude oil. We performed the tertiary low salinity water injection on same sandstone rock. And at the first glance, what you can see is different crude oil would lead to different response to low salinity water injection. It means it actually, this is the crucial factor in determining the impact, the results of the low salinity water injection. The other thing is, we in our system we saw that the maximum oil recovery that we can obtain in laboratory scale can be as much as 10%. The other factor that I want to mention is that if we have checked the repeatability, we have checked that one, and this blue one and this brown one, they are the same crude oil tested on the same rock, and you can see that it's almost on top of each other, showing that our results are repeatable. The other factor that I want to highlight here is that for tertiary low salinity water injection, even in the lab scale, what we saw is it takes around 1 pore volume, let's say less than 1 pore volume, to see the first oil produced by low salinity water injection. So in our experimental approach, what we did, which was a bit novel, that we tried to mix the crude oil to come up with a new blend of the impotent or negative crude oil with the positive crude oil. We mix it with 50-50 to reach to another new crude oil. If we have impotent crude oil, which were negative low salinity water injection, and with very rich crude oil, which resulted in a very high additional oil recovery. And if we get something in between these two, it shows that the content of the polar component, the polar content of the crude oil is actually the determining factor for low salinity water injection. So here there is the results of the tertiary low salinity water injection using 4 different crude oils. This one is the weak crude oil, impotent or negative crude oil in terms of the micro-dispersion formation. And this brown one is the very rich crude oil performing very well in terms of low salinity water injection, and we blend them. One is called mix 2, one is called mix 3. The mix 1 and mix 2 and mix 3 are the ratio of the mixture between the impotent and the rich one. And you can see that by varying the ratio of the blend, you get different results in terms of low salinity water injection. And actually the result is in between these two impotent and rich crude oil that we have used, showing that the micro-dispersion characteristic of the crude oil is actually the main mechanism behind additional oil recovery, and it can be a really useful tool to screen the crude oil before doing any coreflood, before doing any studies in terms of the additional oil recovery by low salinity water injection. So here is very interesting piece of experimental results we can see. So here again we have a potent or rich crude oil with a very high efficiency to tertiary low salinity. Then we have another one which is called an asphaltic crude oil. This is a DP crude oil. It has performed fairly good to low salinity water injection. But we have 2 more crude oils we have. One is blended of this asphaltic crude oil and the potent one. And you can see that adding good components of the rich crude oil to the asphaltic crude oil has boosted its performance, and we have more additional oil recovery. But another one is that we have taken this rich crude oil, we have pre-contacted with the low salinity, and then we carefully remove that brownish phase, which we call it micro-dispersions. And you can see that its performance actually reduced remarkably. You can see that from more than 10%, the additional oil recovery dropped to less than 2%. This would indicate that that brownish phase, that interfacial fluid-fluid interaction, which we call it micro-dispersion, that's actually the main and predominant mechanism behind additional oil recovery. And actually this single slide shows that if we want to screen the crude oil and if we want to identify the positive crude oil, we need to just identify and characterize its potency to form micro-dispersions. So here in this slide, what I have done is I summarize the results of ultimate additional oil recovery by low salinity water injection versus micro-dispersion ratio. So this micro-dispersion ratio is what it is formed after contacting with low salinity water injection divided by this initial bond water of the crude oil before any experiments. So you can see that there is a clear monotonic relationship between IOR by low salinity water injection and micro-dispersion ratio of that crude oil using same rock. So if we have a very low micro-dispersion ratio, there is a very little additional oil recovery. And if we have very high potency of that crude oil towards in terms of micro-dispersion formation, we will get very high additional oil recovery by low salinity water injection. So that this simple curve can show that there is a very direct relationship between the oil polar component responsible for micro-dispersion formation and additional oil recovery by low salinity water injection. So what about carbonate formation? If the predominant mechanism is a fluid-fluid interaction processes, so it should work in carbonate formation as well. So in the next few slides, you'll see the results of the same approach, same methodology applied for carbonate formation. For that, there is a paper published, and I encourage you to go through the paper to see the details of how we perform the experiments and how we get the results and analyze the results. For the experiments performed on carbonate rocks, we use different crude oils, but we kept the rock and the brine same. We analyzed 8 crude samples, and you can see we have the micro-dispersion ratio plotted versus the crude oil number. And we have this crude oil, which is a good crude oil, a very rich and potent crude oil responding to micro-dispersion formation, very good. And then we have other crude oils, relatively negative ones. We selected these number 3 and number 2, and we tested on the carbonate rock to see how it performs. So in terms of the methodology, same one as sandstone one. We used 3 cores taken from a carbonate formation from Middle East. 3 crude oils were used. 1 positive one, as you saw from previous slide, 1 negative one, and 1 which is we use the positive one, and we remove the pre-contacted crude oil and low salinity, and then we remove the interfacial phase to remove the micro-dispersion, and we perform, for the coreflood experiments, we perform secondary high salinity and tertiary low salinity water injection. Again, here I'm showing just the results of the tertiary low salinity. For the sake of time, you can go through the paper and see the results of the secondary water flood. So here we are showing the oil recovery versus pore volume injected for tertiary low salinity. The red one, the solid red one, is for positive crude oil. The green one is for impotent or negative crude oil. And the other red one is, and you see the very flat red one. This is a positive one, but we treated crude oil and removed the micro-dispersion. You can see a very sharp impact of removing micro-dispersion from the crude oil. When we remove the micro-dispersion from this red one, it's actually become a very negative crude oil with no response whatsoever to low salinity water injection. So in addition to the oil recovery, we have tested other hypotheses like pH changes for carbonate. You can see again, the pH is going up for all 3 cores or all 3 experiments similarly, which indicates that the pH variation is not a responsible cause behind the additional oil recovery by low salinity water injection. In terms of the ionic interaction between the aqueous solution and the rock, here I have plotted a calcium to sodium ratio is divalent divided by monovalent ratio. You can see that all the 3 cores, they have similar changes. They going up and then coming up, coming down. Same trends in terms of the sulfate to chloride that we have plotted here. Because the low salinity water is a dilution of the high salinity, the ratio in the injection water is the same for both brines, although the total salinity are different. But you can see that again, in terms of the sulfate, we don't have a conclusive results for the relationship between the ionic changing of the water and additional oil recovery. Hence, the only thing that is controlling the performance of the low salinity water is the polarity or the potency of the crude oil towards formation of the micro-dispersion. So to explain how this micro-dispersion can lead to additional oil recovery and the detaching of the oil from the rock, we have this illustration here. We think that when the oil is changing wettability initially and these polar components are adhered to the rock, when the micro-dispersion is forming by low salinity water, then we will having a dislocation of the polar components because they are surrounding the packet of the water, which we call it micro-dispersion, and then it weakens the bond between the oil and the rock, and hence we have dislodging of the crude oil from the surface, which would lead to additional oil recovery. And therefore, there should be a balance of the forces, which leads to a mobilization of the oil. So how we can quantify micro-dispersion characteristic of the crude oil? The test should be performed in a spontaneous manner, because the micro-dispersion, as we identify from micro model and visualization experiment, they form spontaneously. We should not have any mixing or agitation, because mixing and agitation will trigger the conventional emulsions. But this micro-dispersion, they form spontaneously. Any quantification and characterization should be carried out under temperature, because temperature would contribute and facilitate actually the formation of the micro-dispersions. One thing that we have observed is the micro-dispersion will not break by centrifuging the fluids. So if they form, they are unbreakable unless chemically something is added to the system. In order to quantify the amount of micro-dispersion, Kyle-Fisher titration can be used to measure water content, because the main characteristic of micro-dispersion is this nano water molecules dispersed in the crude oil. Still, the wettability state of the system is very important. If we have a very strong wettability, either water wet or oil wet, in our experiments, we didn't see significant additional oil recovery, irrespective of micro-dispersion formation. So, as a conclusion or synopsis of our talk today, so we have seen that in sandstone and also in carbonate, fluid interactions can be studied for screening the crude oils. Also, we have seen the water film beneath the wetting crude oil may not be as active as it was believed, because if it was active, then water, the double layer expansion, ion exchange, the other important processes can be in play. But we saw that the predominant mechanism is basically micro-dispersion formation. The very solid thing that we identified is, if the oil cannot form micro-dispersion, we would expect negligible additional oil recovery by low salinity. If the oil is very potent towards micro-dispersion formation, still we need to identify the favorable wettability state of the rock in order to achieve the additional oil recovery by low salinity water injection. Thanks for your attention. I would like to thank my supervisors, my collaborators, and students helping me delivering the results and this slides and the talk. Thank you.